I'm very excited to present. Sorry, let me back up. I'm Sarah Fisher. I'm a community engagement manager with the Cancer Genomics Cloud. I'm very happy today to present to you Dave Roberson. Dave is a community engagement manager at Velsera who specializes in scalable and reproducible biomedical analysis. He is passionate about helping researchers maximize the value of new cloud computation technologies, as anybody who has ever come to our academic office hours will tell you. And previously, Dave had worked at the National Cancer Institute's Cancer Genomics Research Laboratory. So with that said, I'm going to go ahead and turn things over to Dave.
Thank you so much, Sarah, for that wonderful introduction. And it's really a pleasure to be here. This is my first time in a very long time speaking at the CGC webinar series. Today, I'd like to talk to you about chest imaging, phenotyping, and machine learning / AI, and how those all can be combined together on the Cancer Genomics Cloud. So let's go ahead and start with an agenda. So I want to cover 3 main areas. A little bit of background in case you don't know much about the Cancer Genomics Cloud. I'll provide that. We'll deep dive into some medical imaging use cases, and then we'll do a live platform demonstration. Please ask questions during throughout. I can see the chat, and if I don't notice your question, I'm sure Sarah will let me know, and then I won't take the whole time. We'll have time for a discussion afterwards. So before I get any further, I always like to do the acknowledgements at the top. So we have 2 people from our BIC staff, or also known as our bioinformatics staff here at Velsera, that were instrumental in creating a lot of these applications and creating these public projects, Nicola and Voya. In addition, I want to mention Dr. Dennis Dean, who has led a lot of the AI and ML initiatives at Velsera. So for external collaborators, we're working a lot with Matt Satosky at the Renaissance Computing Institute at, also known as RENCI, as part of UNC. So we'll showcase some of his work, and we're going to mainly focus on Dr. Raul San Jose Estebar's work. He's a co-lead at of the Applied Chest Imaging Laboratory at Brigham and Women's Hospital at Harvard. So that's going to be what the live demo is about. So the Cancer Genomics Cloud, as you know, it's supported by the NCI, and it's one of the cloud computing resources which are part of the CRDC. And really, one of the main important things is that these CRDC allows you to access these tremendously large hosted data sets, which are really becoming the fuel, what I like to call the fuel for AI and ML research. So we have this tree image, which you may have seen before, which shows a lot of the different branches that provide a lot of the different the data sources. So these can all be connected relatively easily with the Cancer Genomics Cloud. So you can pull in data from the proteomics data commons, the canine data commons, the cancer data aggregator, potentially clinical trial data, and be able to use these for training or fine-tuning of your models. Now, we're going to focus on imaging. So, of course, you have the Imaging Data Commons, IDC, and the Cancer Imaging Archive, TCIA. So you guys really have a unique opportunity to combine multiple modalities to do some interesting machine learning research. So what makes this all possible is this new cloud framework, really. All these are connected together using a lot of services that are provided by the National Cancer Institute. And there's also a new research model that I'm sure you're familiar with at this point. The old model would be that each institution would have to download a copy of their data, a copy of the data, and interact with it on their local environment, right? So that's the old model. Now I will come back to this in 1 second, but the new model essentially is the data will be hosted on one of the cloud providers, and that will be the single source of truth, essentially. And you're going to bring your expertise, you're going to bring your software to where the data resides. And so that's really what we mean by cloud. In addition, you're going to get a lot of efficiencies such as immediate scaling, so you can use multiple cloud nodes at the same time if you need to. You don't have to purchase these expensive machines. And therefore, it levels the playing field, right? So researchers at large institutions are kind of on the same playing field as the smaller institutions or even like the biotech companies. Many researchers can access the same data at the same time because this is all essentially using cloud object storage. And by having the data and the methods in the same place, you start to take a step forward into higher reproducibility and streamlining. Now, I want to circle back to the old model. Sometimes you need to keep your data in the current location. Maybe you're at a hospital. You can do what's called federated learning. It's a bit of an edge case, and we won't get into that, but that will still enable you to sort of have a hybrid setup. So what enables researchers to transition or go back and forth between the cloud and a local environment is having familiar software that will provide a place to create these machine learning models. So this is the super familiar RStudio interface, which includes these 4 windows, source, environments, console, and your plotting outputs. So we have something called Data Studio on the Cancer Genomics Cloud, which is the ability for you to start either RStudio, Jupyter Lab, or SAS Studio inside of your project, so inside of your web browser. And now RStudio and Jupyter Lab, since day one, these are built using HTML and web technologies, and the new version of SAS Studio is the same way. So these will boot up right inside your environment, and these are private only to you and to your collaborators. So we also recommend, what we recommend is getting started with these familiar environments. And then once you're ready to scale your inference using what's called apps. Now, apps are great for production work. So what we mean by that is going from potential pilot study of 100 subjects to over 100,000 subjects. And, of course, that will require more cloud funding, but what you want to do as you transition is to sort of do it in a stepwise manner. And one of the major steps is to be able to codify your analysis into something that's well-defined and portable. And that's where the, two technologies really come into play here. One, you may have heard about the Docker portable containers. So you have the Docker containers, which really enable moving the same analysis from environment to environment, but you also need a workflow description language to be able to piece together multiple steps and to make it runnable by someone that may not have the intimate knowledge of your script. So we'll talk about workflow orchestration languages in the next slide. Another great thing about the apps is that you can use a lower cost machines, which I'll talk about. And really all that's required is that you find a Docker that you trust, either from Docker Hub or make one yourself. And you can use the workflow editor to stitch these steps together. So the image I'm showing down here is one of the workflows in the chest imaging platform. And this actually goes from training to model selection to prediction and reporting. Now, the great thing about this is these are extensible. So if you wanted to swap out the reporting module, you could do that. You could add additional data types and build out this analysis graph. So we have over 1,000 apps that are available in the public apps gallery. And of course you can make your own, but you don't have to because we have them already. So these are great if maybe your expertise is in imaging, but you want to add a genomic modality to your analysis or to your model. So of course we have many genomic apps, including the what I'm highlighting here, the Genesis. The Genesis suite of tools, which are for genome-wide association studies, that include single variant analysis, visualization, aggregate analysis. And the point is that the results of these can be additional features. So those are available to browse in the public apps gallery. And currently they're all common workflow language based, but we are branching out into other workflow orchestration languages, starting with Nextflow. So I want to highlight that our colleague Darko is presenting at the Nextflow Summit at the end of October, and you'll see this being sort of broadcasted or amplified rather on LinkedIn. So he's going to talk about using Nextflow on a 7-bridges based platform and how he worked to optimize the NF core RNA-seq pipeline. So our goal is to have many of the Nextflow core pipelines available in the public apps gallery as well. So what else? So another feature that we have is public projects. And these are great for learning. And in fact, we've used them, Sarah and Rowan have used them in courses that are being taught by using the Cancer Genomics Cloud. And essentially you're working yourself through, in the lab, working yourself through a public project. So a public project you can think of as like an end-to-end experiment. So it's a project which is a container for your instructions, your files, which are your data or your reference files, your apps, potentially you could include some already run tasks, some analysis, for example, and of course, interactive analysis via RStudio or Jupyter Lab. If you have something you want to showcase to the community, we can make your project public. Just email our support staff. But just remember to not include anything proprietary or controlled. And the great thing about public projects, a user can clone the entire project, and that'll get all the components. And I'll show you how to do that in the demo. So there's 3 relatively new platform features that I want to highlight before we move to the next section. And some of these are maybe for more advanced users, but I just want to make sure that we're highlighting these. So with machine learning and AI, one of the major, so the training and inference steps a lot of times require specialized compute. And more likely than not, those are compute that are enhanced with the graphical processing units from one of the NVIDIA machines. So of course, Amazon and Google and Microsoft are providing these machine types. So we have these available now, or very soon, using so the new series are the P4 series, G5 and G6. So this is kind of really technical, so don't worry too much about it. And in fact, if you're running an app, you don't have to worry about this because you can hard code what machine it should use. But if you're a developer, it's important to know that a P series, or in this case a P4, will be great for training tasks. And G5 or G6, they're a bit lower powered, but still GPU enabled. And those are great for deep learning inference. And why this is important is because there really are a dramatic price difference. So when you're thinking about, optimizing your cloud funding, really only use P4 for the more expensive training, and then using the other ones for prediction. In addition, so that's for Amazon. We also have similar machines available on Google Cloud because the Cancer Genomics Cloud is a multi-cloud platform. So that's the first one. The second one is, you may have heard of this term, I've said it a couple times before, which is the spot market. So spot market is a great way to save and conserve your cloud funding. You can actually save 80% of the cost. So if you're using your pilot funds, you can save 80% of those by just always using spot market. I highlight a dramatic example of the P4. They're rather expensive. The on-demand could be $32 per hour. But just imagine using those sparingly and also using the spot market, you could save 80% of that. But it's across the board. And the caveat is that the cloud providers will only allow you to use it until the demand for the higher price gets to a certain point, and then you'll be preempted. So the new feature that I'm highlighting here is the ability to get preempted, which will happen from time to time, but then allow your pipeline to wait until it can reacquire another spot machine. And you can fine tune this. So you could say, I want to try it 4 times, and if I get preempted 4 more times, just just run the rest of it on the full price because I need my results by tomorrow or something like that. But that's much more customizable than it was. Now, to use this effectively, you need to also think about how can I run my traditionally longer running workflow in a way that could be interrupted and I'm not going to lose all my work. So this is really one of the major steps to make your analysis cloud ready. So think about frequent checkpointing if we're talking about training, machine learning training, or if we're talking about more traditional workflow, think about running things in a highly parallel fashion. So both of those will help you be more resilient. So the final new feature I want to talk about is Data Studio Environment Safe. So this is the most highly requested feature. So if you've come to office hours, everyone says, I really wish I could do this, and now you finally can. So, in previous times, when you have a Data Studio environment, RStudio, Jupyter Labs, SAS, obviously all your data would always be saved in your current workspace. But if you installed a new package, a new version of a package, or something similar, you'd have to reinstall that next time as one of the requirements. Now you can actually decide to save a new version of your environment or save over top of a previous version. And that's what this animation is showing you. So you can have multiple versions and you can share it with other colleagues in your project. I've also found that this works really well with Git or GitHub. Previously, if you cloned a project in your workspace, it had trouble with the timestamps. But now if you sort of clone a Git repository outside of your workspace, you can save the whole environment, restart it. The next time you could commit your changes and then push your changes, and it will be seamless with Git or GitHub. So those are the 3 new features, kind of technical, but let's talk about some medical imaging use cases that we're going to highlight just at a sort of a high level, and then we'll do a live demonstration of one of them. So regardless of the use case, Python, as you may well be aware of at this point, is critical. It's really the open source Python libraries are making much of machine learning and AI possible. And I want to highlight 3 ways they do that, or they help with image segmentation. So you have open source libraries, OpenCV and Scikit image. So example of this would be differentiating between lung disease tissue. So here we have some images from provided by our collaborator, Matt Satuski at Renzi. So these actually, it's not a cancer use case, but you can imagine that it would still be applicable to determine not only where is the lung tissue in a CT image or X-ray, but where is the healthy tissue and where is the disease tissue. So this is one that we frequently use in a college level training that we give. So it trains on open data and it's able to understand, you're able to segment and label where the lung tissue is in a CT image. So you also have, things like feature extraction. Maybe you want to do, you need some more data to train on. So these are example would be quantitative images from a chest CT scan, measuring size of lesions or tumors using scikit-learn. And then finally, how Python's critical to integrating all of these, such as using an example would be using the TensorFlow pipeline in to predict COPD progression. So some more examples. So we have 3 of these. These are either available as apps or Data Studio. The first 2 are Data Studio. So we have MC Micro, which is the end-to-end processing of whole slide imaging and tissue microarrays. So it's, and Sarah and Rowan know much more about this than I do, so they're here to answer questions. But these will be for whole slide images. We also have PyImageJ as a public project. So this is a really interesting use case where it's taking traditionally a Java-based desktop application, ImageJ, and it's making an interface that's in a notebook format. So that's what it's showing you here on the right side, is you're able to interact with ImageJ using Python commands and sort of learn how to use that, but in the privacy of your own project using CRDC data sets. And finally, we have a sort of an older app called SVG Deep Learning Image Classification. So these are available in the public apps gallery as 2 CWL apps, one for training and one for prediction. You can actually combine them in the same workflow if you want, but these are an example of an easy to run training and prediction system for image classification. So we also have a collaboration of Velsera with the National Heart, Lung, and Blood Institute. So we have 2 projects which started out on a platform called Biodata Catalyst. I've already mentioned these before, but we have a COVID-19 image segmentation data studio analysis, which was created by the team at RENCI at University of North Carolina, Chapel Hill. So we talked about that. That's great for really learning about how to train a model to do image segmentation. I highly recommend this as well. We can give you more information about that. Just let us know. And then we're going to go into detail about the automated chest imaging platform, which was a collaboration between Velsera and the Applied Chest Imaging Laboratory. So those are 2 collaborations that started out as Biodata Catalyst and HLBI projects, but then have been ported over to Cancer Genomics Cloud. So let's dive deeper into one of them, which is the chest. And thank you for all the links, Sarah. We're going to dive deeper into the chest imaging platform. And one of the main use cases for the chest imaging platform is for analysis of COPD. So COPD stands for Chronic Obstructive Pulmonary Disease. So it's a category of diseases that's defined by inflammation in the lungs, and that causes obstruction. So there's 2 main types, chronic bronchitis and emphysema. And it can be diagnosed using a lung function test called spirometry, or as X-ray or computed tomography, otherwise known as CT scans. So where the chest imaging platform comes in is, how do we digitize this? How do we use machine learning or AI to be able to predict progression of COPD earlier and earlier? And you can imagine, any type of lung tissue, so even lung cancer. This is a question for this community. Could you use the chest imaging platform to diagnose progression of lung tumors? So currently the software is enabled as a public project on Cancer Genomics Cloud. So it includes 7 apps. So the first step is conversion. So generally CT scans are provided as DICOM images. There's a different file type in this public project, but the first step is conversion. So there's conversion app, which is a NERD to HDF5 format. Then there's a COPD training, COPD prediction app. Then there's 3 apps for vascular densitometry and airway analysis. And then there's the workflow I previously showed you, which is COPD end-to-end deep learning workflows, which does training and selects the best model, then it does prediction. And there's 2 interactive notebooks, staging using deep learning and a k-means subtype clustering. And here's the link here, but I think Sarah potentially already posted it in the chat. She did. So that was my last slide. Now I'd like to switch over and do a demonstration of the Cancer Genomics Cloud. And I want to focus on 3 things. 1, how do you access the platform? Which is really the first hurdle. Then how do you train and run an ML model via an application? Because it's a very easy way for you to get started in using your pilot funds is to run one of the apps. And then how to start up a private data studio machine learning environment to dive into the commands. The notebooks are really great to dive into the commands and then start to modify the notebook to suit your own research purposes. So I'm going to zoom out here. As you can see, I'm in my web browser now, but I'm going to switch over to the first website I want to show you, which is cancergenomicscloud.org, which is a website that we maintain. It's got a lot of great information about for learning about the Cancer Genomics Cloud, videos, learning resources. You can either register for the CGC, or you can go ahead and just click launch. I log in with my ERA Commons ID and password, but there are multiple ways you can log in. You can also choose a email and password, or sorry, email password. Just you have to verify your email address. So if you haven't seen the CGC before, this is sort of what it looks like. This is what it looks like. You have all your projects you may be involved with on the left side, and then your most recent analyses on your right side. You have some information about public data, and then some really helpful getting started links, which I think this is really great. And at the bottom of every page, since I always mention this, you can get some context-specific help documentation, and then contact our support directly this way. So we're going to be focusing on one of the public projects today, which can be found under the Public Projects tab. So these are the current public projects that we have, and we're always working to add more here. And like I said, if you have something you want to showcase, just email our support team and then they can recreate it for you in a public manner. The first one is the most recent one, which is what we're going to talk about, which is the automated chest imaging platform. But some of the other ones I mentioned are here as well. The PyImageJ, variant annotation apps is another good one. I didn't talk about it though. Introduction to SAS, Cancer Data Aggregator is a great one. MC Micro that Sarah put a link to in the chat. MoPow is a great one. This was created, I believe, by the Mirzaman lab at NCI. And this is another way to think about doing multi-omics, combining multiple modalities. And there's another breast cancer multi-omics analysis using the Diablo framework. So there's a lot of really good stuff to look at. So when you click on one of the projects, you'll see it as it is in its public form. You can browse through everything here. It always has a nice description, and then in many cases, some tasks that are already worked through here, as well as files. The first thing you want to do is click on the extra information icon here, the eye icon, and click Copy Project. And then Sarah mentioned in the chat that Um, so in the chat, you can select your pilot funds, and Sarah mentioned that you can get up to $300 in pilot cloud credits. Of course, if you belong to other um, pilot funds, feel free to select one that's appropriate. I've already copied this, so I'm just going to show you that. But then you could, of course, rename the project. I could say this is Dave's version of the automated chest imaging platform, and you click copy. And then it makes you a copy of all the features of the project. So I already have this copied, and it's part of one of my projects. So I just want to orientate you to what a project is like. And it's exactly what the public project is, except you get a membership panel here. So I can go ahead and invite some of my colleagues. Invite Rowan. And if you know their name and you've invited them before, their name should pop up here. And then, of course, you can fine tune their permission levels as you see fit. So now I have my colleague here. I want to sort of show you some of the different things we have in the public project. So we have files. The files tab everything is pretty much files based. So these files are actually links to, in this case, it's the Amazon bucket, which has these as object-based storage. So this doesn't contain any of the DICOM images. It starts out with everything as an NRRD file, and these are the chest CT labeled images. But it also has some phenotypes and some reports from. So this is the input file. So these are tagged as input data NRRD. Whenever you see a histogram, that means it's a report that you can view without downloading. So you have all of these files that you can use as part of the app. So let's look at the apps really quickly. So these are these should be 7 apps, 1, 2, 3, 4, 5, 6, 7 apps that were sort of using the chest imaging platform software, but have been described in the common workflow language, which means in this case that they are fully parameterized and they're intelligent to know what machine type it should use. And in general, it's easier to run than trying to run the command line. So, for example, you can run training then prediction. So if you want to learn how to run any of these, you can simply just click on the app itself, and then it will give you a description as well as the required inputs, some of the settings which are required, which may not be required, and the expected output. So you're going to get for this training app, you're going to get a H5 file which contains the weights and is what's considered the best training model based on the algorithm in here. You also get some accuracy and loss plots that are viewable as an image, and then another report that's based on the CSV. So this has already been run, and I just want to show you how easy it is to look at the outputs and then also rerun the app with different parameters. So every time you run a task, a task name is sort of auto-generated. But you can change that if it helps you with organization. So we have COPD training run. So let's look at the parameters here. So it's just using the input data, COPD staging, deep learning sample data in the H5. So you had to run NRRD to H5 first. And then these were the settings which were used. So it had a batch size of 5 and a number of epochs, which was 10. And then only save the best model was set to true. So let's say I looked at the results and I wanted to run some more epochs just to see what the loss function would look like, sort of potentially overtraining it, right? Just as a learning example. I could just click edit. If you notice, I clicked edit and rerun. It saved all the parameters here. But what I could do here is simply say we're going to do 30 epochs. And I've changed the name of the task. And I'll change this parameter to 30. I think if you click on these question marks, the default is 100. So that seems really high to me. But you know, even if you don't fill these out, it can still run because a lot of these are have default values. Including image size. Okay, so let's say I wanted to save all versions of the model. I could toggle that as well, and you click run. And if you wanted to see what components or what resources the machine was using, you can always go back and check that. So if I wanted to see the training run, I think it will still save it even if it was from a public project. Let's see if I'm correct or not. Yes. So, you know, these are sort of based on sample data. So this is not taxing the systems in any way. Let me zoom in here. So you always get this timeline starting from 0 seconds. In this case, it just took 7 minutes to do the 10 epochs. And then you see the machine type it's using. So in this case, it's using a P3. And if you remember, this is the previous generation. We now have a P4, which is going to be even more capable. But this type of thing it's great for learning. It's not really going to tax the system. You can also see some some metrics here. What I do wish that we add, and maybe we will in the future, is to see the number of GPUs that are being utilized and some more information about that. But this is traditionally just showing you the CPU and RAM disk. So, you know, these are training data sets, so it's not really taxing the system. So I'm just going to check the chat. Thanks, Sarah, for answering some questions.
Yeah, we have a question from Paul Lee, who's very interested in how to use the applied chest imaging platform apps and Python code for a small research question. And I think you are actually gearing up to show us your data studio session, right?
Yes.
Yeah.
Yes, that's what I would like to end with, the data studio. And yeah, it's good. Thanks for the GitHub link. Fantastic. Okay, so we talked about cloning the public project, and we talked about running apps to create these tasks. So the 30 epoch is still running, but I bet you it'll finish just in a few minutes. But the front door I'd like everyone to go through is what's called Data Studio. So Data Studio is the ability to run JupyterLab, otherwise known as Python notebooks, RStudio, or SAS. So I have 2 of these that are running. So this shows that you can have sort of multiple environments that are tuned for different things. So one is for using deep learning, and one is for k-means clustering. But if you want to make a third, you know, feel free, and you can have these saved and starting up at different times. So here's the different sort of environments you can pick from. OHIF viewer is also something that could be really helpful for imaging viewing. So if I wanted to make a third one, like a scratch environment, I suppose. And then the next thing is you pick the image setup. So we have these are the different stock environments, right? Now, one of the newer features that is coming out is you'll be able to have custom environments as well. So the default, and this is something that needs to be updated, but the default for TensorFlow and PyTorch is this environment, which has an older version of Python. It's still easy to update, and then with the new custom data studios, you'll be able to save the new version and rename it as well. then you can pick the machine. So we have C4 series and C5, and C6 should be coming out soon, which are the compute optimized. But then we have P3, P4, and then G5 and G6 series as well. So if you wanted to do some machine learning, this list needs to be updated, and it will be soon for Data Studio, but the other machines are available for running tasks. This will give you an idea. So right now, obviously, now I've seen always start with the lowest possible spec machine until you're ready, especially with GPUs, because the GPUs, they're generally at a premium. And then a lot of times you don't need multiple GPUs to do what you need to do. So this one just has the one GPU. So for the working space, you generally don't need more than, I would say, 200 gigabytes or so. So you can fine tune that, because remember, the data you're accessing is hosted by NCI. So you're not paying for any of that storage. What you want to do is to try to avoid conversion as much as possible. I know that's not always possible, but regardless, that's going to be stored in your project. That doesn't count against this attached storage. So this is just sort of working storage, scratch storage. And then you can set a suspend time. So this is an idle timeout. I usually increase it to about 60 minutes, and then you click start. So this will take 2 minutes to boot up. Now I have two that are running right now. So I can show Paul some of what it looks like to be running. So I want to show, I'll just pick this one, the subtype clustering. And when it opens, you'll see that this is a fully featured Jupyter Lab environment. So you can have
Dave,
multiple nodes.
could you zoom in a couple ticks?
Oh, sure. Yeah. So this actually is and I get this question a lot. I just want to access a terminal. Like I don't even want to start with the notebooks. You can start this up, and then you have I gotta zoom in here. Oops. So you have a fully working terminal here. It's a little bit different because you're not using like PuTTY, or I forget what some of the other Linux SSH tools, but this does give you all access to your project environment. So, oops, did I not spell it right? Oh, Sarah has a great video that goes over this structure. So here's all the files that you have access to, but are not actually located on this running machine. So you can access the H5 files, the different CSV or NRD files as well. So, you can of course create multiple notebooks here, or you can go through this phenotype clustering notebook, which was created by the chest imaging laboratory. Now, in this case, okay, so this case is actually going to walk you through something that is very BDC related, but that's okay. You don't have to rerun this. You could just read the code. In this case, it's downloading phenotypes from a Biodata Catalyst node. And then a lot of times you still have to install some new software, and then you can do the k-means clustering here. If I wanted to flip back to the other environment, which is the deep learning environment, I can open this one. So this is another running on a totally different server. And in this case, it was one that was using the P3 series. So in this case, we have the model weight saved here. So this is showing you the different, here, let me zoom in, showing you the different epochs including the final model. So this one is actually going from, this is the checkpointing. My understanding of a checkpointing is what I was talking about, is saving the different epochs. So then you could go back and later and create an accuracy plot. But if we go back up, it actually has a Python notebook, which shows you how to create the convolutional neural network. Still doing the old style of installing the requirements first. Like I said, one of the new features will be able to have you skip this step because you won't have to install those. It shows you how to load the pre-processed images. So here you can just preview some of the images in the array. And then here is an example of the model, which it's going to help you build, which is a combination of CNN and LSTM. So you have the neural network plus the temporal ability of the LSTM. So last stuff, not getting too much into the details because that would take probably another 30 minutes. But well, we'll have time for discussion, but I just wanted to provide some additional thank yous to my colleagues, Sarah and Rowan. Here's our email addresses. Feel free to email any of us if you want to try this out and you need some more sort of guidance. Some of us will be at ASHG, which I know is not till November, but it'll be in Denver. Please reach out in person there, or of course, set up a quick call with us and we'll gladly jump on.